Hi everyone, and welcome to another video of this channel. So today is a very special video because we will be proving the famous Euler's identity e to the I pi plus 1 equals 0 without using Taylor series. So this identity, it's special because it connects the five, you can call them fundamental constants of math, right? E, I, pi, 1, and 0, which are all very fundamental in calculus and imaginary numbers, and so on and so on. But traditionally, this is proven with Taylor series, but today we will take a different approach with some other branches of calculus. So first, we will look at the integral of 1 over 1 plus x squared dx. It seems like a weird way to start, but this lead will be quite fruitful eventually. So this is equal to the arctangent of x plus c, or the inverse tangent function of x. So just a quick proof of this, note that the derivative of the tangent of the arctangent of x, right, the tangent of the arctangent of x is the same thing as x. So this is just equal to 1, this derivative right here. Then we can use the chain rule and simplify, right? The derivative of tangent and secant squared times the derivative of arctangent, right, derivative of inner function, equals 1. So the derivative of arctangent of x equals 1 over secant squared, which is just cosine squared, of arctangent of x. And now we can draw a little triangle to see how this looks like. Right, if this angle right here is the arctangent of x, remember, the arctangent of x refers to an angle, that this thing must be x and this must be 1. Then the tangent of this angle right here would actually lead to x. And then this hypotenuse right here, by the Pythagorean theorem, is the square root of 1 plus x squared. And so the cosine of this angle is this side right here over this side right here, which is the same as 1 over 1 plus the square root of 1 plus x squared. And so the cosine squared is 1 over 1 plus x squared. So we know that the derivative of the arctangent is equal to this, so the integral of this equals arctangent. Like that. And now we will actually look at this integral in a completely different way, using partial fraction decomposition. And how will we do that? Well, notice that 1 plus x squared can be factored into x minus I and x plus I. Notice for this integral, we do indeed have a polynomial 1 over a polynomial with a higher degree, which means partial fraction decomposition can be used. Right, we can factor the denominator like this, and then rewrite this big integral into the partial fractions. And so once we find a and b, we can just write this in this form right here, x minus I plus b times natural log of x plus I, just like that. And plus c, of course, right? But first we have to find a and b. So if we have this fraction is equal to the sum of these two fractions, we can multiply both sides by x minus I times x plus I to get this right here. And then we can consecutively substitute x equals I and x equals negative I to get a equals 1 over 2i and b equals negative 1 over 2i. And then we can substitute these numbers into the result for our integral. So we can use log rules and combine this. And we have that this integral is equal to 1 over 2i times natural log of x minus I over x plus I plus c. And so we can combine the results from these two sections to get an identity. Arctangent of x equals 1 over 2i ln of x minus I over x plus I. But we have to be careful, because arctangent of x has a plus c, and this right here has a plus c. They don't have to be the same c. So these expressions right here only differ by a constant, which isn't necessarily 0, so we really have to be careful about that. And on a quick note, I also wanted to mention that this isn't an equation for x. This is an identity for x. So like this is true for every real x. So for x equals 1, this is true. For even x equals 0, this is true, right? So how I said earlier, right, that this differs by a constant, we want to find that constant. So we plug in x equals 0 to this true identity, and we get that arctangent of 0, which is 0, equals 1 over 2i ln of negative 1 plus c. So c equals negative 1 over 2i ln of negative 1. So see, it isn't 0. We really had to be careful. We would have gone a different identity. And so we have that arctangent of x equals 1 over 2i times the natural log of 1 minus x over I plus x. I'm sorry, I minus x over I plus x for all real x. This is like an identity. And I mean, this is really beautiful. This is a very interesting relationship between arctangent and the natural log. And this might actually be useful for calculating strange arctangent values. However, we want an identity connecting exponential values e and trig pi. But right now we have an identity connecting inverse trig and inverse exponents. So we do a variable change and substitute x equals tangent of z. So z is just another variable that is defined as the arctangent of x. So z equals 1 over 2i ln of 1 minus tan z over I plus tan z. I'm sorry, I keep saying 1 minus tan z. I minus tan z over I plus tan z. So we have I minus tan z over I plus tan z equals e to the 2iz, right? If we multiply both sides by 2i and then exponent each side by e, we get e to the natural log, which is just this inside, and then on the other side, e to the 2iz. So we, again, have this beautiful identity that connects tangent with e. So this is approximately what we want, right? This is an identity for z. We could have any other variable in here, just like x or something like that. So this, in general, we can try interesting values of z just to see what happens. So if we try, for instance, z equals pi fourths, right, we're trying to get a convenient value of tangent of z, and z equals pi fourths yields e to the I pi halves, and then I minus tan of pi fourths, which is 1, over I plus tan of pi fourths, which is again 1. So we have e to the I pi halves equals I minus 1 over I plus 1. And then we can factor an I out of the numerator, and we have I times I, which is negative 1, plus I times 1, that's I. So this factorization works over I plus 1. These cancel, and we have I. So e to the I pi halves equals I, and if we square both sides, we get that e to the I pi equals negative 1. And so, if we move the 1 to the left-hand side, we get our beautiful Euler's identity, which this can also be considered Euler's identity, but this is like a more aesthetically pleasing form of Euler's identity. So, I hope you like this video. Thanks for watching, and I'll see you next time.